Hello, these are the solutions to the Chapter 6 review number 1. So we're told here chromium has an anomalous configuration. You wouldn't be expected to know that it has an anomalous configuration, but we're told here that it does. How many unpaired electrons does the atom contain? Okay, so what we would do for this question here is imagine we'd have a 4s subshell and a 3d subshell, and that these subshells simply have 1 electron in the 4s, 5 electrons in the 3D. So collectively we have 6 total unpaired electrons. Which statement is true about the photoelectric effect? It says a metal may release electrons when it is irradiated with light with a high enough intensity. It's actually not true. We need light to have enough energy per photon. So a metal may release photons when it is radiated with light with a low enough wavelength. E is equal to hc divided by lambda. So if I use a low enough wavelength, that gives me a higher energy. That's sounding correct. Although a metal may not release photons, it's actually going to release electrons. So a metal interacts with light with appropriate energy to become ionized and release electrons. So statement B almost was right, but we're releasing electrons here, not photons, when the metal is struck with light. So a metal may release photons when it's irradiated with light with a low enough wavelength. That sounds right. Probably the right answer. Let's make sure a metal may release electrons when it is irradiated with light of a high enough intensity. We can't just use a high intensity light that doesn't contain the right wavelength to cause the electrons to be ejected. We have to use light that has the proper wavelengths of light or the proper frequency. So we want to use light that has a low enough wavelength or a high enough frequency. Because again, we want to go to a low wavelength to go to a greater energy, or we want to use light that has the higher frequency, higher energy of the photon. We need the photon energy to be high enough. So we have to go to a lower wavelength or a higher frequency than the specific frequency or wavelength associated with the minimum energy it takes to remove those electrons. So what is the de Broglie wavelength of an electron moving with a velocity that is 1.0 times 10 to the minus 3 times the speed of light in nanometers? Okay, now our equation here for the wavelength of matter, or sometimes I call it lambda d for the de Broglie wavelength, it's h divided by mv. Okay, and so then the velocity is this amount times the speed of light. So the velocity of the electron here is going to equal 1.0 times 10 to the minus 3 times the speed of light. Well, let's be a little bit more precise and call it 2.998 times 10 to the 8 meters per second. So this should equal 2.998 times 10 to the 5 meters per second. So that's going to be the velocity that we plug in. Now, in the days where I got to write my own midterms, I would have an equation sheet that would have the mass of the electron, usually in units of AMU and kilogram given. Sometimes quizzes or exams might give you the mass of the electron in grams. Just to trip you up, we got to put this mass into kilograms. And the reason why just has to do with the units of H. So units of H, we're going to use the ordinary unit, 6.626 times 10 to the minus 34. Now a joule times a second is a kilogram, meter squared per second squared, and then the second is still times seconds. So this is our joule, and then times seconds. And so because of the kilogram here, we want the mass of the electron to be in kilograms. Now you would like the problem would give you somewhere within the problem. Usually it would say, like the electron mass is, whatever. And it might trip you up, might give you grams, might give you AMUs where you have to do the conversion. But the key is that we'd use the mass in kilograms, 9.109 times 10 to the minus 31 kilograms, and then times the velocity. So we want the velocity in meters per second. So the per second here cancels with these seconds. One of the meters units cancels. The kilogram unit cancels. The only unit that doesn't cancel is one of those lengths there in meters. And so if we do the arithmetic here, 6.626 times 10 to the minus 34. In fact, why don't I just wave the magic wand? Once you get I have the key here on the side, so I don't have to waste too much time on the video working out just the solution. But we end up getting 2.4 times 10 to the, would it be minus 8 meters, and converting over to nanometers, getting 2.4 nanometers. Just remember 1 nanometer, 10 to the minus 9 meters. So nanometer is really small. Okay, so once we get the length out in meters, we just convert over to nanometers and answer accordingly. Okay, what is the ground state electron configuration of a sulfur atom? So sulfur is in the oxygen group, next atom down. So if we're starting from the 1s, you could follow along on a periodic table. Just a 1s2, 2s2, 2p6 gets you through neon, 3s2 gets you through sodium and magnesium, and then sulfur is 4 over, so we're going to be a 3p4. Which transition of an electron in the hydrogen atom could cause the emission of a photon of the greatest wavelength? Okay, so let's look at some of these and let's remind ourselves the one key detail that we're expected to know here is that the 1 to 2 is the greatest energy difference, then the 3 is a little bit lower, then the 4 is a little bit lower, then the 5, and the 6 even lower. So these would be the relative energy levels for the 3, 4, 5, and 6. And so we have a few different transitions given. So we have a 3 to 4, so it looks like this one here, that requires the absorption of energy. So go from low to high requires the absorption, not the emission of a photon. So 1 to 2 is going to be out, because again, that's going to require the absorption of energy. Up here is our infinity. If you keep going up, you get to infinity. So the 1 to infinity corresponds to the ionization energy. Obviously, that transition is going to require the absorption of energy as well, not the emission of energy. Then we got the 4 to 3 coming down. Let me put this in red. So we got the 4 to 3 versus the 2 to 1. So the 2 to 1 is definitely the greater energy transition. The 4 to 3 transition is definitely the lower energy transition. But the lower the energy, the greater the wavelength of that transition. So the greatest emission is going to come from these transitions from the 4 to 3 transition. Moving on to page 2. Question 6 actually gives us information to calculate a wavelength associated with the energy. So we have an ionization energy of sodium is 496 kJ per mole. An experiment similar to Hertz's experiment. He was the one who took light and was shining it on a metal and seeing you needed a certain frequency of light or energy of light to cause electrons to be ejected. That led to the description of light as containing photons and coming up with the equation E is equal to h nu, E is equal to hc divided by lambda. And so anyways, if it takes 496 kJs per mole to ionize sodium, then what's the wavelength associated with that transition? Then what wavelengths do you want to use? Greater than that wavelength or lower than that wavelength? Okay, so what we might want to do here is say, well, what would this energy be per photon? Or excuse me, what would the energy be per sodium atom? So for one sodium atom, how much energy is required for it to be ionized? Well, it's 496 kJs per mole of sodium. 1 mole of sodium, 6.022 times 10 to the 23 sodium atoms. We want the energy just 1 atom of sodium. And then if we're going to want to plug this into an equation using Planck's constant in joules times seconds, we're going to want to convert over to joules. So 1 kJ, 1,000 joules. And so let's actually work this one out here. So we got 496 divided by Avogadro's number. Times 1,000. So I got 8.239 times 10 minus 19, call it 8.24. And so then this energy here relates to the energy of a photon by h nu or hc divided by lambda. So if we want the wavelength associated with this transition, we'll take hc divided by that energy. So we want our photon energy to contain at least this much energy. So we want our energy to be greater than hc divided by nu. And then when we cross multiply nu, we need our wavelength to be less than to go to a lower energy. So again, lower wavelength, greater energy. So when we cross multiply, we got to flip the sign, or just think logically about what wavelengths cause a photon to be ejected. It's going to be lower wavelengths than the one we calculate here. So wavelength energies of 8.24 times 10 minus 19 joules or greater energy could cause a photon to be ejected. So I'm going to take H 6.626 times 10 to the minus 34 times 2.998 times 10 to the 8, and then divide by this energy. I get 2.41 times 10 to the minus 7. Put the sign wrong. So we want lambda to be less than 2.41 times 10 to the minus 7, or to be less than 241 nanometers. So if sodium is radiated with radiation with a wavelength lower than 241 nanometers, then the sodium atom can become ionized. Moving on to number 7, write and balance the oxidation reaction between aluminum metal and nitric acid. Okay, so that'd be Al. I don't know why I want to change my pen color. Okay, so let's go aluminum solid plus HNO3. This is going to form AlNO33. This is water soluble. The acid's water soluble. And then the product here being H2 gas, which actually would just float away from the reaction solution. If I want to balance here, I'm going to get my 3 nitrates. And then I would need 3/2 O2. So I might double everything to get rid of the fraction. So I might have 2 aluminums, 6H plus, giving me 2 Al NO33s, and then 3H2. Okay, so I wrote balance the reaction. How much half molar HNO3, so 0.5 mole per liter HNO3, is needed to dissolve 27 grams of aluminum? So 27 grams of aluminum is about 1 mole. It's like 26.99 something. So this is 1 mole of aluminum. For every 2 moles, we need 6 moles of HNO3. So if I want the number of milliliters of my HNO3 solution, number of liters, not milliliters. So with the number of liters of the HNO3 solution, I start with my 1 mole of aluminum. For every 2 moles of aluminum that are present, I need to add 6 moles of HNO3. And the HNO3 solution is half molar. So I have 0.500 moles of HNO3 per liter of that solution. So it looks like we're going to have to add 6 liters. That's what this works out to. So we need to add 3 moles of HNO3 to react with the 1 mole of aluminum, and it's half mole per liter. One of the keys in all of these problems that involve molarity is recognizing that this just means 0.500 moles of HNO3 per liter of the solution that contains HNO3. So sometimes explicitly writing this out is more helpful than using the M. So I had to write it out so I can get the right mole of HNO3 to cancel, moles of aluminum to cancel to get me to liters of solution. Moving on to number 8, what type of orbital is occupied by an electron with the quantum numbers 5 for N and 3 for L, and how many orbitals of this type could be found in a multi-electron atom. Okay, so our L is telling us the shape, so we have the 0, 1, 2, 3 for the shape of the orbital being S, P, D, or F. So this is going to correspond to a 5F orbital, and the number of the 5F orbitals is given by the range of m sub L for the subshell. So the range of m sub L takes the minus L to plus L, so minus 3, minus 2, minus 1, 0, 1, 2, and 3. So 1, 2, 3, 4, 5, 6, 7. So there should be 7 5F orbitals. Now the 14 is how many electrons you could get into the orbital. The D's would have L's of 2. The P would have an L of 1. Which atom below does not contain a total of 7 valence electrons? Okay, so iodine does, so it's not the answer to the question. So iodine does have 7 valence electrons. All the halogen group does. So the halogen group has like an NS2, NP5 configuration. So like fluorine is a 2s2, 2p5. Iodine ends up being, what would it be, 3, 4, 5, 6. So like a 6s2, 6p5 configuration. Now once you have a filled F and D subshell, those don't count towards the valence. So we have 7 for iodine, we have 7 for fluorine. Nitrogen only has 5. Nitrogen's configuration is a 1s2, 2s2, 2p3. Outermost shell only gets us to 5. So these 1s electrons don't count towards the valence. Now manganese, let me do the configuration down here. Manganese is in the 4th row, so its configuration would be the argon configuration followed by a 4s2. Then it's 5 over in the 3D subshell. So manganese has 25 electrons. It's a 25th element. So 18 plus 2 plus 5 gives us 25 electrons distributed. And then our valence count rule, outermost shell. So we have 2 for the 4s subshell for the outermost shell, and plus these 5 in the lower unfilled subshell. So 7 valence electrons for manganese. So iodine, manganese, fluorine all have 7 valence electrons, so nitrogen's the only one here that does not contain 7 valence electrons. Moving on to the final page of this packet, how many total valence and core electrons does a tin atom contain? So that's Sn. And so tin is, I believe, element number 50. I'm going to pull up on the side here, just look at, double check my periodic table. So it's also in the row of carbon. Just making sure we get the right atomic number. Yep, element number 50. This tells us we should have 50 electrons distributed or shown in our diagram. Tin's in the 5th row, so its configuration can start with krypton. That's 36 electrons, followed by a 5s2. Gets all the way across the D subshell for 10 electrons, and then it lands in the 5p2. So it's like carbon. Carbon's an ns2, np2, or 2s2, 2p2 for carbon. And we get the same count for valence electrons. So our valence shell here are just these 4 electrons. These 10 don't count towards the valence once the D shell is completely filled. So we have 4 valence electrons, and the only reasonable choices are B and D. Now the core is just the remaining. Everything that's not a valence electron is a core electron. So then we have 46 core electrons. So 4 and 46. Consider the ground state electron configuration expected for the atoms below. Which atom contains the most unpaired electrons in its ground state configuration? Okay, so titanium is a 4s2. These are all on top of argon. So all these configures are the argon, then a 4s2, 3d2, vanadium is a 4s2, 3d3, iron is a 4s2, 3d6, nickel's a 4s2, 3d8, and then zinc is a 4s2, 3d10. Okay, interestingly for zinc is the only one here with 2 valence electrons, because now it has the completely filled d subshell. All the others have way more, so if we just, the question doesn't ask for valence electrons, but just making sure we see that titanium has 4 valence electrons, we have 5 valence electrons for vanadium, we have 8 for iron, and then we have 10 for nickel, but then only 2 for zinc, because it's the only one here with the filled d subshell. Now, iron's going to be the one that ends up with the most unpaired electrons. So for iron, we have a 4s2, and then a 3d, I have my 5 3d orbitals, so make sure you start with 3d orbitals, and you have 5 of them. So 1, 2, 3, 4, 5, then 6. So iron has 4 unpaired electrons. Vanadium only has 3. Titanium has 2. Nickel has only 2. So if we look at nickel, nickel would have a 4s2, and then 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8 for the 3d8. Zinc would have 0 unpaired electrons. So the most in these atoms here would be iron. The most in the 4th row of the periodic table would be manganese, because it has that 3d5 configuration, so it ends up with 5 unpaired electrons. Technically, chromium's more, but you have to know that it's anomalous. I wouldn't expect you to have that predicted, but chromium actually has 6. We saw that on the opening question on the packet. Okay, so which of these sets of quantum numbers is not possible for an electron in an atom? And so what I'm looking here is for a set of quantum numbers that has something wrong with it. So 2, 0, -1, plus a half. This is what's wrong. The -1 can't happen. If an L is 0, the only m sub L that's possible is 0. Because the range of m sub L is its own L value, negative to positive. So the only possible L value is 0. So which set is possible? Well, 1's not possible. 4, 2, plus 2, minus a half. That looks good. So 2 is definitely possible. 5, 3, 0, minus a half. That looks good too. Nothing wrong there. So 3 is possible. 2, 2, 0, minus a half. The range of L, it only can be up to n minus 1. So the highest L can be when n is 2 is 1. So L here can be 0 or it can be 1. That just means you can have the 2s or the 2p subshell. You can't have a 2d subshell. 3, 1, -1, 0. The spin can't be 0. Electron has to be spinning, either backwards or forwards, either with or against the magnetic field, either up or down. The up or down isn't necessarily up, isn't necessarily plus a half, but just one of them is the spin up, one of them is the spin down electron, or the plus half, minus half. So the spin has to be one way or the other. It's never 0. So it can't be 5. So it can't be 4, can't be 5, can't be 1. So only 2 and 3. All right, that completes the activity.